Thank you for coming to watch this video. I did notice that my last one was quite popular in regards to some of my other ones. But I apologize for my shortcoming recently. I recently have had exams, which has caused me to obviously not be able to attend to this channel as much. I have not forgotten about it. It's just I've had more demanding things to do recently. But I have noticed that this series I have begun, these numbered series of me talking about the functions and stuff of the brain, has been quite successful. And nonetheless, today I will be talking about neuroplasticity, arguably one of my favorite topics within the brain as a whole, and exploring how this is basically just exploring how the brain modifies its structure and function in response to stimuli. So, for example, you could talk about on the microscopic level, like individual like synapses strengthening or weakening based on activity patterns, or let me just name some levels that you guys would have to get used to. So maybe the mesoscopic level, like neuron clusters adjusting their connectivity to optimize processing efficiency. So that just sounded like a bunch of words, but in simpler terms, it's just neurons adjusting themselves to be more efficient. And on the macroscopic level, so a larger scale, it's just the entire brain regions shift functions based on demand or damage. So, more effectively, this dynamic process allows humans to acquire new skills, recover from injuries, and adapt to changing like environments or events in their life that has caused something. I will be going over a case study, and if you want to pause, you can put in the comments what case study you think I'm going to go over. A hint is that neuroplasticity can also be linked to healing of damage to the brain. Okay, now the definition of neuroplasticity. So, it's basically, as I said, the brain's capacity to adapt structurally and functionally. Well, capacity, you could say capacity because it is how much it can do, but it's functionally to experience an injury. So, the thing is with this can occur multiple ways. So, synaptically, so let's see. So, for example, synaptic remodeling, changes in the strength or number of synaptic connections that are within the brain. This also links to network level modifications. This can also be linked to dendronic or dendritic changes or attraction, for example, and axonal sprouting, so extension of new axons to compensate for lost pathways if damage has been done, which led to that. So I will be going over the types, but those are some. So it can be long term or short term in terms of structural or synaptic. And it really just looks at the remodeling of neural circuits in the brain, since think of the brain as just a big bundle of wires, and if one of those wires are cut, for example, some people that are paralyzed from the waist down, that's because imagine a wire has been cut and the signals are no longer being able to be transferred through that part of their body. Okay, now types of neuroplasticity. It's basically just I'm trying to think of a way I can pronounce this easier to you, because the thing is, with structural plasticity, it is just, if you look at the word, you will know it's physical changes, but it's just in the architecture, growth, or elimination of connections, more simply. Like, for example, dendritic growth. Like it could also be called synaptogenesis, as I've heard before. And also there's another process called aberration, and it occurs in response to experience and learning. So neuroplasticity doesn't always have to respond to damage. So like, for example, when you're working, like if you go to the gym or something and you're building a muscle, for example your bicep muscle, many tears occur in it. I'm gonna say this very generally. Many tears occur in it, and then when your body repairs it, that's when the growth occurs. This is basically what's happening when you're learning in this sense. So, like for example, musicians would have like denser synaptic connections in motor neurons due to the repetitive practice, because they are constantly learning new ways to play the instrument. Now, functional is basically the redistribution of neural functions, and this is more just actively between brain regions and to optimize processing more. This can, however, occur like naturally by learning a new skill by choice or pathologically, like if you want to. Like, if say if you're finding your way around somewhere, your brain's gonna remember where your house is. Obviously, I'd hope. So, if you got lost, you would obviously have an idea. Or if you're completely lost, obviously this wouldn't apply as much. But for example, blind individuals, they would have developed a heightened auditory processing as the visual cortex recognizes, like, well, not really the visual cortex, it will just respond to sound and other senses more easily, as this is the functional plasticity that had occurred. So I hope you're becoming more comfortable with the definition of plasticity now, and neuroplasticity, neuro just means the brain, as I hope you know. So plasticity is just reparations basically. And finally, one of the main, there's many million types of plasticity, but for the sake of this video I'm only going through the three main types. So it's just the brain's ability to reassign functions to undamaged areas when injuries occur. So that's the way I can probably say it. So post injury, yeah, so it's just basically after injuries occur, like after stroke patients experience like a stroke, obviously their brains would adjust their regions to regain motor functions most of the time, or they would go into coma and the plasticity hadn't occurred, which is why this is either short term or long term. Now, moving into mechanisms, not really mechanisms like in chemistry type of mechanisms, because those are probably one of my favorite type of mechanisms to learn about and talk about honestly so far within my A level thing, but let's not get out of track here. So let's see, sorry, where's the mouse? Hebbian plasticity, yes. So in my experience of my research in this topic, this is basically just like a type of learning that strengthens synapses through repeated activation. So some people would study using active recall, I believe, and this is basically a very high consistent, I don't want to say like you're taking advantage of Hebbian learning and Hebbian plasticity as a whole, as it strengthens your synapses through repeated activation. You're actively learning, do you understand? So it's just this consistently doing that. But here's where it gets a bit more complicated. So I'm gonna keep this quite simple, but this is more of a overview. So LTP, I'll refer to it as LTP, but long-term potentiation. It sounds quite confusing, but it's just weakening of inactive synapses. Okay, I'm saying the word synapses a lot, but I'd hope you do actually know. It's just the gap between two neurons. So it would basically, the vesicle would get allow the transmission of an impulse between the neurons. So it's basically just something that allows the impulse to go through it more simply. So anyways, LTP is basically the persistent strengthening of synapses through increased neurotransmitter release. So the synapse is responsible for allowing it to go across it, the neurotransmitter chemical, and receptor sensitivity. It's very critical for memory consolidation, actually, the process of turning short-term memory into long-term memory knowledge. So yeah, you don't want to keep anything in your short-term memory practically. It's just people that are studying for long amounts of times and effectively would want to have good use of this LTP type of neuroplasticity mechanism, as you would like to say. But long-term depression, so it's not the depression where you get like very sad and you go on antidepressants type of depression. It's just basically a different type of depression where it's the weakening of inactive synapses to optimize efficiency and prevent unnecessary energy expenditure. So I said that in quite a confusing way, but in other terms, the reason I'm always going to say in other terms and other terms and other terms like this all the time is because a way of understanding the brain and really becoming fond of the ideas surrounding the brain's functions is particularly through simplifying things and then expanding on it later. So I said reducing unnecessary energy expenditure. So, for example, in photosynthesis, yeah, about 1% of the light from the sun is used for that, well, is actually absorbed by the plant. And then about 60% of that is used for respiration, and 40% of that is used for photosynthesis. So, with that analogy here, I'm just showing that most of the energy that our brain would use whilst doing these impulses could be dissipated, so not used to its maximum extent. So, like for example, plants would have a lot of chloroplast because they would want to absorb the most light without letting any go to waste. So, with that photosynthesis analogy, it's basically just preventing unnecessary energy expenditure. So maybe stop it, like reducing the amount of, for example, possibly you could say, so it's basically like removing the resistance of a wire so the current can flow easier. If you're a physics student interested in this. But yeah, it helps refine networks and eliminate redundant neural connections. So that's basically the main thing behind that. Anyways, sorry for stopping quite long there. I just wanted to find a word which was perfect for me to use there without giving false information. Anyways, let's go to neurogenesis. It's basically a generation of new neurons, primarily in the hippocampus, which I had gone through last time, facilitating learning, memory, emotional regulation, though at a much lower rate than during early development in your brain. So that's basically it. So let's go on an overview quickly. So long-term potentiation is just strengthening of synapses to increase neurotransmitter release. So stronger impulses, basically, more efficiently, could say. These are all for like efficient neuroplasticity, more like. And long-term depression, so LTD, is more the weakening of inactive synapses, so that the needed connections would be the strongest. Neurogenesis is just generation of new neurons. And I don't go over the Hebbian plasticity as much because it is quite simple in the way that it's just the strengthening of synapses through repeated activation, so active recall, basically. Now, it gets very compiling here. Let's put a very easy slide to understand here, but there are multiple molecular mediators in this process which support synaptic growth or regulate gene transcription required for long-term memory storage. So basically the CREB receptor molecule, and they basically all have a purpose in neuroplasticity. Think about it. So they all mediate neuroplasticity. So let's start with this here. BNDF, synaptic growth. Okay, so this is very, very, very simplified. But the thing is, this supports synaptic growth, neuron survival, and I'm very bad at this. Dendrons, dendrons, just dendritic branching. So if you wanted to support the release of this mediator, And actually, before I even get onto this, carry on with BDNF. BDNF stands for brain deprived neurotrophic factors. Or factor, sorry. And basically, exercise and enriched environments enhance BDNF expression, which strengthen neural pathways. So basically, it's just all the growth of a synapse. So all of the synaptic growth you could experience would be mostly due to BDNF, as when you do exercise, this is also released in a sense. Anyways, so CREB, I like to call it. So the thing is, this is just a response element binding protein. So the CAMP we're going to learn about in other videos, lowercase c and big AMP, capital. And it's basically, the reason I'm not going to tell you now is because it does get confusing if I make the word too big, but it's a response element binding protein. Let's look at the word response element binding protein. It regulates gene transcription, as it says here, and it facilitates basically the transcription required for long-term memory storage. CREB activation facilitates protein synthesis necessary for stable synaptic formation. So obviously transcription would lead to translation due to the formation of mRNA. And this activation would basically allow for stable synaptic formation. Now, one of the final more important molecules in this is NMDA receptors, which mediate calcium influx, triggering intracellular signaling cascades that reinforce synapses more, basically. So, let's see. LTP regulation, if we go back here, it's basically just the fact that so it does have quite a bit of roles, but NMDA, what it does to LTP, it practically allows further strengthening of synapses through increased neurotransmitter release and receptor sensitivity. So this NMDA would be essential for learning adaptation, especially in LTP related memory formation. So as I said, LTP would be useful for memory consolidation in terms of turning short-term to long-term memory. And this would in turn mediate many things, such as calcium influx, which trigger intracellular signaling cascades, as I said, reinforcing synapses, and it would be essential for learning and adaptation. That's basically it. It just releases or regulates LTP in a sense. Now, developmental versus adult plasticity. So I should have said back here adult neurogenesis to do with the hippocampus, because it's not adult in terms of you'll see it's just a critical period where the sensory input sculpts brain connectivity through synaptic pruning. Now the thing is with this is developmental, so sensory input just shapes the synaptic shape, for example, so sensory input. And adult plasticity is less pronounced due to inhibitory factors like myelin associated proteins, and learning and adaptation can still occur but require more repetition and intense engagement for strengthening the new connections. For example, that was an example of adult plasticity. Back to developmental, it's basically when the language, it depends on early exposure. So for example, post-childhood, your language learning would become more difficult because sensory input when you're young, so when you're developing, it sculpts the brain more than if you're older because of proteins associated with myelin. Now, an example of this is stroke rehabilitation. It can take months or years because adult brains reorganize more slowly because the brain's already used to the environment it has put itself in. So, as I said, language acquisition and post-stroke recovery. Clinical applications, stroke and TBI. So, here the thing is, there is multiple types. There's multiple types of clinical applications of this. You can use it for axonal sprouting, where new pathways are formed to restore lost functions. So this is cortical, basically just like the organization of corticals which enable recovery. And CIMT therapy promotes remapping. So CIMT is just constraint-induced movement therapy. It's like forces use of impaired limbs or strengthening weakened neural pathways to encourage cortical remapping, improving motor function or recovery. So like if you're into physiology, or like say if someone had recently experienced a coma, they would have to go to a physician where they would have to learn how to walk again, for example. And this would be hard due to, as I had mentioned, adult plasticity is much more slow due to inhibitory factors such as myelin associated proteins. And another thing is basically, I always mess this word up. It's like parallelizational cortical remapping. There we go. It's just like neighboring brain areas compensating for damaged regions. So like say if a part close to the frontal cortex is like the prefrontal cortex, I say even more forward in your brain, is damaged, then something close to it, so a small part of the brain close to it, would have to check the job that it has to ensure that the functions are still able to take place that are important for survival. Now, if you guessed right and you made it this far in the video, you do see Phineas Gauge, and there's another head up there. Is hemispheric trimetry. Sorry, not trimetry. I was just studying chemistry. Sorry, hemispherectomy. So it's just functional compensation in children. Basically, this hemispherectometry. I need to really learn how to pronounce my words today. Hemispherectomy is basically just when it just shows remarkable compensatory like plasticity with the remaining hemisphere assuming like lost functions. So basically it's just showing like a case of evidence for this neuroplasticity like even occurs in the first place. It's like damage to a child's brain is like more successful, like to obviously its full healing capability is more successful fulfilling its full healing capabilities in young individuals more than old due to heightened neural adaptivity. Now, HNA, heightened neural adaptability, sorry, it's a factor. So there are multiple factors to things, obviously. So like the myelin associated protein would also be a factor, but that's also just a factor. I'm just saying the most common ones. So basically what the hemispherectomy in children shows is just it showed more remarkable compensatory plasticity in younger children due to the high HNA, so heightened neural adaptability. Phineas Gage's case study. Let's look at this now. So, as you remember, there was a metal pole in a rock. TNT exploded it, and it went straight through his prefrontal cortex and those parts of his brain. I did do a whole case study on him. So if you would want to see a more deeper version of it, then comment down below. But it's basically he faced that damage, and it led to a dramatic personality and behavioral change. But it provided early evidence that cognitive and emotional functions are linked to brain structure. However, he did also heal from this, which also is an idea of neuroplasticity, mainly due to the fact that his brain was able to like repair itself. So like it's basically just an example of all of this, because not really looking at LTP or LTD or anything like that, it's like he was still able to survive with this, and he didn't like struggle from a stroke or anything. And this is quite remarkable because it really shows how functional plasticity, structural plasticity, and compensatory plasticity all comes together. So it reassigned his functions, obviously. So this is an example of compensatory plasticity. So it's able to reassign functions to undamaged areas when injuries occur. Functional plasticity, where it was the redistribution of activity between brain regions. Obviously, his frontal region was completely damaged, so it was redistributed. The main act of it, like the main activity of the prefrontal cortex, was changed. It was over time he got better, and it referred to like the physical shape of his brain was changed, and there was obviously scans to show this. Now, with this, experience dependent plasticity. So enrichment leads to dendritic growth. Taxi drivers would have a larger hippocampus. Now, if anyone has any idea why, I do know why. Let me know in the comments, because you would have to watch my previous video to know why they would have a larger hippocampus. This is all just neuroplasticity, so adaptations, brain adapting. So the brain adapting to support whatever job the person requires to do most, in a sense. Musicians and expanded motor cortex. I'll go over this cortex in another video. So, but this just shows how if you're enriching someone, you're going to have dendritic growth. Taxi drivers, their neuroplasticity is going to lead to a larger hippocampus, because they obviously need to have intense spatial mapping required for navigation, so they need to learn and remember a lot. And musicians, they would need to show increased motor and auditory cortex activity due to their skill refinement. And this just illustrates as a whole that the brain physically reshapes itself based on repeated experience, enhancing function and favoring adaptation. Now, to enhance your neuroplasticity, because it is a big part of our thing of living, like if we want to live, I would really promote you, or really just provide my condolences that you really should take these factors into mind, maybe. So exercise, cognitive training is very strong for this. Sleeping a lot, you need to sleep 8 hours. Meditation is very good for calming you down, and exploring I'll go over that in another video actually. This is a very good point. I would need to have a whole separate video on this type of intervention. But more simply, it's basically just, in other words, you know what, I think I would have to go through another video on this, because honestly, this is too big to condense this type of thing. But it basically will just improve your attention and regulation and emotional control, basically. Okay, now to finish this off, I would need to go over the considerations and everything of plasticity. So maladaptive plasticity. So it's basically when we encourage the plasticity ourselves. So overreactive synaptic pathways reinforce pain perception. So chronic pain. If you have plasticity and say that you have a functional thing, plasticity, and then obviously this assigns more, like this leads to more pain receptors being activated, it would reinforce these pathways and you would feel pain more intensely. Phantom limb syndrome, so this is another ethical issue. Abnormal sensory remapping, like if you remap it by yourself, if doctors do it, it could decrease, or like when you amputate something, it leads to the illustration of like maybe you feeling something that isn't there. And you might have heard about this before, because it is a very common symptom in amputees. Neuroenhancement ethical issues is more like TDCs are a big problem in technologies, as well. I'll actually tell you what it is. It's just transcranial, like direct current stimulation. So it's basically, it raises questions of cognitive equity, and the long-term effects are uncertain, and it could possibly induce abnormal plasticity rather than improving function. So too much plasticity can be a problem as well, the same way that if a cell divides, cool, it will lead to growth and repair. But if that growth of a cell is abnormal and uncontrolled, then that's cancer. Oh, sorry. Anyways, that's the end of the video. So a lot of mishaps today, but this was quite a hard topic to go over, and this is basically just the main takeaways. Is just central to learning, memory and rehabilitation, and there's a lot of advancements which you can read in this box here. Comment if you would like to connect. Thank you for watching. I'll try my best to be more consistent, but I can't promise anything for these next 2 weeks, primarily due to the fact of my UCAS exams approaching. So, thank you for watching. If you would like to connect, please comment. Thank you. Goodbye.